Okay, we're going to look at solving this differential equation. So although we might be in a certain chapter and so you might know what kind this is, part of what you want to think about is bigger picture. When you're faced with any kind of differential equation, how do you know how to approach it? So the first thing is classify the differential equation. So pay attention to independent and dependent variables, order, and then linearity and homogeneity. So we see the derivatives here, so we know that y is the dependent variable. That means x must be the independent variable. We've got a second derivative, that's the highest order derivative here. This is the second order. The question about linearity would have to do with what is applied to the dependent variable. So the dependent variable y only has differentiation applied to it and multiplying by functions of the independent variable in each term. So this is linear. And because the right-hand side, when I've got it written with the dependent variable all on one side here, the right-hand side is not the zero function. This is non-homogeneous. So second order linear non-homogeneous. All right, so we know some things about the structure of the solution. The solution is going to be of the form y is equal to yh plus yp, where y is a solution to the associated homogeneous differential equation, and then yp is any particular solution to the original differential equation. So the first thing we might think about is finding the yh. And so to find the yh, we're going to need to solve the associated homogeneous differential equation. Okay, so depending on the form of that, then you're going to use whatever strategy is appropriate for that. So for this one, I'm going to first of all notice that I unfortunately do not have a homogeneous differential equation where all the coefficient functions are constant. If I did, I could use a characteristic polynomial, find the R values, and pretty much write down the solutions pretty quickly. But because I don't, I have these variable coefficient functions. There are some other strategies that I'm going to have to think about with that. I might notice I do not have initial values, so although Laplace transforms maybe could work, that is challenging when you do not have initial conditions to plug in. So I have variable coefficient functions, no initial conditions. So this is kind of the type that we've been working on in the chapter to do with series solutions. So that is a possible strategy, but there is one other thing that we talked about in that chapter to pay attention to that sometimes works when you can avoid using the strategy of the series solutions. So this is of the type of equations where we found series solutions, but one thing that you might notice here is that this is actually a Cauchy-Euler equation. Remember, a Cauchy-Euler equation is of the form a x squared y double prime plus b x y prime plus c y is equal to 0. This is a second order Cauchy-Euler equation. You can have higher order ones as well. And those are a little bit simpler because you can actually solve those by making a substitution and then hopefully finding two linearly independent solutions which generate the entire solution space for that. So when you recognize that it is of that form, so it's sort of quadratic in form almost, where the degree on the variable squared here, independent variable squared, is equal to the order of the derivative on the dependent variable in the same term. So sort of quadratic in form, or if it was higher order, cubic in form or whatever. So those ones are a little bit easier though. So for Cauchy-Euler equations, remember that you can guess y equals x to the r and just figure out what the r values are that make the equation work. All right, so let's go ahead and do that much for this one. And just to save space, I'm going to go ahead and write the derivatives across here. So y prime then would be r x to the r minus 1. This part is the same every time. Take the appropriate derivatives. And then you're going to substitute that into the differential equation, the associated homogeneous differential equation. All right, so I'll have x squared times this second derivative if you've done a few of these, you might go ahead and recognize that you can simplify every single time you do a Cauchy-Euler equation. This first term is going to simplify with the powers on the x. So once you recognize that, you can maybe skip a step and just don't make mistakes in the algebra there. But all right, so x times y prime are x to the r minus 1, and then minus 3y. And then if that's going to be true for all values of x, then the coefficients are going to have to be 0. So the nice thing about this kind is that when you make that substitution, all of the terms end up with x to the r. And so you can factor out that x to the r. And so you're going to be left with r times r minus 1, x to the r. I'll go ahead and pull the x to the r out on the back end here. And then the second term, I have x to the 1 times x to the r minus 1, which simplifies to x to the r. So I'll have minus r. And then I've got my x to the r factored out, and then minus 3. And so if that's true for all values of x, then this polynomial has to be equal to 0. We call that the indicial equation sometimes. So I don't care if you remember that vocabulary, but the key thing is that this equation has to be equal to 0 in order for this equation to be true. So solve for r, multiply this out, combine like terms, refactor. I'll go ahead and write that stuff out here. Sometimes I skip those steps, but I don't want to mess it up. So r squared minus r, and then minus another r will be minus 2r. Minus 3 is equal to 0. So you'll factor that into r plus 3, r minus 1, and you'll get r equals negative 3. Nope, you're going to factor that into r minus 3, so you'll get r equals positive 3. And then the other factor will be r plus 1, so you'll get r equals negative 1. I said I didn't want to make a mistake, but I'm trying to save space. So, okay, so those should be the correct r values. Yeah. And if you're not sure, remember you could always put in those r values and take the appropriate derivatives and verify that it makes the differential equation true. All right, so that gives us, fortunately, these are different numbers, and they are not non-real numbers, so distinct real r values. So I get two fairly simple linearly independent solutions to the differential equation, y equals x to the third, and then y equals x to the negative 1 as solutions to this homogeneous differential equation, which means then all of the solutions to the homogeneous differential equation can be written as a linear combination of those. So c1 times x cubed plus c2 times x to the negative 1. So that's going to be my YH part of my solution. So I'm going to put a circle around that so I don't lose it. But then I have to figure out how to find the YP. All right, so kind of thinking back through different things that we used before for higher order differential equations. We've done a lot of stuff with higher order differential equations here. Maybe remember variation of parameters, and that actually works here. So I'm going to just write a couple notes here, and then we'll do the work for it over here. All right, so in variation of parameters, your YP is going to be of the form U1 times Y1 plus U2 times Y2, where the Y1 and Y2 are these two basis functions that generate this solution space, so x cubed and x to the negative 1, whichever one you want to call it, Y1, and the other one is Y2. Your U1 and U2 are functions, and they have to satisfy a system of equations. And the system of equations is U1 prime Y1 plus U2 prime Y2 is equal to 0. U1 prime Y1 prime plus U2 prime Y2 prime is equal to the function that's on the right-hand side of the differential equation. So in this case, it's 1 over x. I think we called it f of x in our notes when we went over that. So you solve this system of equations, or you can memorize another formula that basically is what happens when you solve this system of equations. And so I don't care whichever way you do it. I tend to remember this better than that other formula, so I tend to do it this way. All right, so we're going to use variation of parameters to go ahead and find the other solutions that I need here. So I'm going to do my work over here. So U1 prime times y1. I'm going to call this one y1, and I'm going to label that so I don't forget. And I'm going to call this one y2, and I'm going to label that. So u1 prime times y1 plus u2 prime times y2. I'm going to go ahead and write that as 1 over x here so that the algebra is maybe a little bit simpler as I solve this, or I don't make mistakes, and that should be equal to 0. And then u1 prime times y1 prime, so the derivative of this will be 3x squared. I'm going to go ahead and put my 3 out front here, plus u2 prime times the derivative of 1 over x, or x to the negative 1. So that's negative 1 over x squared. So I put my minus sign out front here, 1 over x squared. So that came from the derivative of x to the negative 1 is negative x to the negative 2, and then is equal to whatever the function is on the right-hand side of the differential equation, 1 over x. So you want to solve this system. And so there's a lot of methods for solving systems. Pick what looks like it's going to work best. The way I often do it, if I don't see anything else obvious, is to take the first equation and isolate either u1 prime or u2 prime. Because you have 0 on one side, that's always going to be fairly straightforward to do. Substitute into the other equation and then solve from there. So I'll just go ahead and do that here. I isolate u1 prime. So this first equation tells us that u1 prime is negative u2 prime times 1 over x, and then I'm going to divide through by x cubed, so that'll be times 1 over x to the 4th. And then I'm going to substitute that into the second equation in place of u1 prime. So I'll have that second equation all in terms of u2 prime. So this second equation will be, I need to be careful here about the negatives and the coefficients, so 3 times negative u2 prime times 1 over x to the 4th minus u2 prime times 1 over x squared equals 1 over x. I almost made a mistake here. I almost lost this x squared here. Right there. Okay. So the reason I caught that mistake was because I had already done this problem, and I remembered that these terms end up being similar. So they both end up with a 1 over x squared when you simplify that. So I'll have a negative 3 u2 prime times 1 over x squared minus 1 times u2 prime times 1 over x squared. So simplifying these. So those two are like terms and end up combining to give me negative 4 u2 prime times 1 over x squared is equal to 1 over x. All right, so we're making progress here. So I need to find u2. So I need to isolate u2 prime and then integrate both sides with respect to x. So I'm going to do some of those steps together. So multiplying through by x squared, I'll just write out here to the side what I'm going to do. I'm going to multiply through by x squared to isolate the u2 prime, and I'm going to divide through by negative 4. So you can think about it as multiplying through by negative x squared over 4. All right, so I'll have u2 prime is negative x over 4, or 1/4 x. All right, so that's u2 prime, so I need u2, so I'm going to integrate both sides with respect to x. So I'll have u2 is the integral of this. So I'll get negative 1/8 x squared, or I'll just make negative x squared over 8 plus c technically, but we talked about when we did variation in parameters why you can neglect the plus c at that step. Has to do with the fact that I already have these c's over here, and so they can be absorbed into that in your answer. All right, so there's my u2. I also need u1. I'll do that here in a little different color, maybe so it'll show up. What do I have here? Pink. All right, so I'm going to go back up to here. Be careful here. This is where I tend to make mistakes if I'm not careful. I'm going to substitute in here so that I can find u1, but be careful that you're substituting in u2 prime. That's here and not u2. I see a lot of students substitute in the u2 that they just got, which I will need later for my answer, but that's not what I need at this step. I need u2 prime. So being careful with your notation, I've made a big deal about that all semester long so that you can grab the right thing. All right, so u1 prime is equal to negative u2 prime. So the negative of this, so that'll be positive 1/4 x times 1 over x to the 4th. Yeah, okay, so I'll end up with 1/4, 1 over 4 times x to the negative 3. I'm going to write it like that since I'm going to integrate here. X times 1 over x to the 4th is 1 over x cubed, or x to the negative 3. All right, so then to find u1, I will integrate that with respect to x. So I'll have 1/4. And then the integral of x to the negative 3 is x to the negative 2 over negative 2. So I'll go ahead and put that down here on the denominator. So x to the negative 2 is the same thing as 1 over x squared. So I'll go ahead and write it like that. So negative 1 over 8x squared. All right, we are almost done here. So yp, we were using variation of parameters to find yp. So this is the form of our yp. So yp is going to be u1, so negative 1 over 8x squared, times y1. This is where your labels help. Oh, there's my y1, x cubed, plus u2, negative x squared over 8, times y2, x to the negative 1, or I'll write that as 1 over x, just simplifying fractions. It'll be a little bit easier here. You could really leave your yp in this form, but I'm noticing that there is a lot of nice simplification that could happen here, so I'm going to go ahead and do that. X squared and x cubed cancel, leaving x, x and x squared cancel, leaving x. So I have a negative x over 8 term, and then another negative x over 8 term. So those are like terms. I can add the coefficients. Negative 1/8 plus negative 1/8, negative 2/8, or negative 1/4 x. Negative x over 4. All right, so there's my yp, and then I need to go ahead and write my overall general solution to the overall differential equation. At this point, it's just a matter of writing it down because I've done all the hard work, right? So, all right, so my overall general solution is going to be of this form: y equals yh plus yp. Okay, and that represents all solutions to the original differential equation. All right, so reminder of something that we haven't done for a little bit, and hopefully connecting some ideas from a couple different kinds of problems that we did in different parts of this unit. All right, thanks.